So, guys, having looked at higher order differential coefficients, then I would like us to now look at Leibniz theorem. Okay, so if we have a function y, which is equal to uv, where u and v are both functions of x, then we can carry out the differentiation of those functions using the product rule. And by so doing, we see that if you are to get y prime, then using product rule, you'll get u v prime plus v prime u. If you are to get y double prime, you differentiate this using product rule, you'll get this two, and this using product rule, you'll get this two, which basically simplifies to this. Differentiating this using product rule, you'll differentiate this two, you get this two, you'll differentiate this, you'll get this, and you'll differentiate this to get this. So this simplifies to u third prime of v and so on. And if you are to get the fourth prime, it will basically simplify to this. Now, notice that from equation 8 all the way up to 12, it is seen that the nth derivative of u increases by 1, moving from left to right. Okay, so nth derivative of u is increasing, and then the nth derivative of the nth derivative of u is decreasing all the way. And the nth derivative of v is increasing by 1, moving from left to right. So you can see the one for v is increasing. V is increasing. The coefficients, like this last one, the coefficient 1, 4, 6, 4, 1, are clearly the normal binomial coefficients that we already know from the binomial theorem. In fact, like if we are to have, you see, this is our y is uv. Our y is uv. If we were to generally have uv raised to power n, that is basically uv nth prime. Okay, we are differentiating it n times. Then this may be obtained by expanding u plus v raised to power n from the binomial theorem. As you can see here, this is uv fourth prime of y, and our y was uv, and we clearly get it by the binomial theorem formula. So it will ideally be the same as this, such that if we are to have y nth derivative, and the derivatives, I'm writing them in brackets so that it's not confused with the power. This is to power n, this is the nth derivative. Okay, this would give us uv, of course, raised to power n, which is the same as us using binomial theorem to expand u plus v raised to power n. And this would give us u raised to power n v plus n u raised to the power n minus 1 v raised to power 1 plus n into n minus 1, all this divided by 2 factorial, u raised to the power n minus 2, v raised to the power 2 plus n minus 1, n minus 2, all this divided by 3 factorial, u raised to the power n minus 3, v3, and so on. Call this equation number 13. This equation number 13 is a statement of Leibniz theorem, which can be used to differentiate a product n times. So So let's look at a couple of examples. Okay, guys, so we are being given determine the nth y nth prime when y is given by x squared exponential 3x. Now, for a product uv, the function taken as u is the one whose nth derivative can be readily determined. V is the one whose derivative reduces to 0 after a few stages of differentiation. So that's one thing to note. Oops. So what's going to be our u and what's going to be our v? Now, if you look at x squared, if we are to differentiate x squared, we will realize that its third derivative is going to be 0. Okay, so our x squared is going to be our v, and our u is going to be our exponential 3x. So we will take our u in this case to be equal to our v to be equal to x squared our v to be equal to x squared, since it's the one whose derivative reduces to 0 after a few stages, and the third derivative of this will give us a 0. And then our u will be equal to exponential 3x. Since the nth derivative of u is clearly known, we already looked at getting the nth derivatives from the higher order powers, the general ones that we were looking at initially. The nth derivative of this using the formula will obviously be 3 raised to power n exponential ax, that is exponential 3x, if you can remember. Okay, fine. So using Leibniz theorem, that is equation 13, our y raised to power n is equal to, now I really don't want to write it again. Let's just go back so that you see it, so that you see the theorem that we are using to rewrite this. that I don't have to repeat it over and over again. So here it is, our equation number 13. Our y is equal to u raised to power n v plus n, u raised to power n minus 1, v1 plus n minus 1 over, so this is what we are using, this equation 13 here. Our Leibniz theorem. Okay, so starts all the way from here, moving forward. So using Leibniz theorem, we know that our yn is equal to that. So where in this case, our v is equal to, put in mind that now our v is x squared and our u is exponential 3x. Now the first term is u raised to the n prime, or u raised to power n. Okay, so what's our u? Our yn will be equal to our u raised to power n. And one thing we need to note that v is equal to, this is the value of our v, yeah? If we differentiate it the first time, what do we get? We get 2x. v2, we get 2, okay? v3 will get 0. That's what, let me write it here so that we have it in mind. If we differentiate v for the first time, so differentiating this, v the first time, the derivative will give us 2x. The second time, the derivative will give us 2. The third time, the derivative will give us 0. Okay, now what is our yn? Our yn, we begin off with the u, and our u is raised to power n. Actually, raising to power n basically means we are finding the nth prime. And we know that from the power series that we did, higher orders, we found that the nth prime of the exponential function is given by this. So we can decide to now start writing. This will be the 3n exponential 3x multiplied by v. What's the value of our v? Our v is x squared plus, from the formula we have n, so n multiplied with u raised to power n minus 1, and that will be 3n minus 1 exponential 3x, the nth minus 1 derivative, and then multiplied with v1. I hope you guys are following the formula. Our v1 is 2x plus, following the formula, we have n minus 1 over 2 factorial multiplied with un minus 2. That is the nth minus 2 derivative of u, and that will be 3n minus 2 exponential 3x. This is multiplied with the value of v in this case is v3, and our v3 is what? Our v3 in this case is 0. So this is multiplied with 0. So this basically simplifies to the nth prime of this product vu will be given by 3. If we simplify this, so we are going to have this, the whole of this is going to give us a 0. So this is going to give us exponential 3x this is 3n minus 2 exponential 3x into 3 squared x squared plus n into 3 into 2x plus n into n minus 1 plus 0. And this ideally translates to our yn being equal to exponential 3x, 3n minus 2 into 9x squared plus 6nx plus n into n minus 1. So ideally, that is what it simplifies to. What is important is that we remember the binomial theorem, because basically if you're having your y being equal to uv and you want to get the nth prime of uv, where u and v are both functions of x, and you want to get their nth prime, then it's very important for you to remember the binomial theorem, because getting the nth prime of uv is just the same as you evaluating u plus v raised to power n. However, remember that the powers in this instant, the powers are basically the derivatives. At this instant, the powers are now the derivatives and nothing else. So when you're evaluating the derivatives, it's also important for you to be able to know what to choose as your value of u and what to also choose as your value of v. From the formula, you should be able to choose your value of v as the one whose derivative reduces to 0 after a few stages, and u is the one whose nth derivative can be readily determined. And from the power series, higher order power series that we looked at, we clearly saw that we could be able to determine the nth series of most of the terms, because I already gave them to you. So you guys can write that. So ideally, guys, all the way up to here, we already have our answer. These last two steps, we are just simplifying because clearly 3n, 3 raised to power n minus 2 exponential 3x is common in all the terms, because you see this is goes in here and it also goes in here. So that's why we've factored it out here and simplified. Okay. So in a similar manner, you guys can work out this example. So let's have it as our example number 2. So find the fifth derivative of this. Find the fifth derivative of this. So let your u be equal to sine x and your v be equal to x raised to power 4 for reasons we already know, yeah? Because the derivative of this, we know very well that in a few stages is going to be 0, okay? And we also know the nth derivative of this. So let's go, guys.